This conference will now be recorded.
So we were learning dual nature of radiation and matter. We have already learned photoelectric effect, and we have seen that photoelectric effect could not be explained by the classical electromagnetic theory. Okay, or in other words, photoelectric effect could not be explained by the wave nature of radiation. Okay, so then Einstein put forward his idea, and that idea was taken from Maxwell's quantum idea. Okay, so Maxwell, when he was doing experiments with radiation, black body radiation, he proposed that electromagnetic radiation could be composed of particles or pockets of energy rather than wave. It is having wave nature, but sometime radiation can act as particle. Okay, sometime wave can act as particle. Sorry, just a minute. So we have seen dual nature of radiation so far. Okay, so what we have seen? We have seen dual nature of radiation. Now today we'll see even matter also can have wave nature. When radiation can have a particle nature, particle means a matter, right? So we'll just discuss a little bit wave nature, where we have seen wave nature of radiation, that is like say interference, then diffraction, polarization. These are the experiments we have seen where we had to consider the light or electromagnetic radiation as wave, and photoelectric effect, and any light matter interaction happens. In those cases, this radiation acts as particle. Like one more experiment you may learn in your higher classes, that is Compton effect. Okay, that is nothing but elastic collision, okay, between radiation and electron. So this is how, when we see there is dual nature of radiation, then there will be a natural question whether matter also can have dual nature. Matter has its particle nature, whether it can also have wave nature. So when radiation has wave nature as well as particle nature, okay, particle nature, that means radiation has dual nature. So natural question is whether matter also exhibits dual nature. Matter also exhibit dual nature. Matter means it has already particle nature, so we have to see whether it exhibits wave nature or not. So to answer this question, de-Broglie, he made a bold hypothesis in 1924. French physicist de-Broglie, French physicist de-Broglie put forward the bold hypothesis that material particle in motion should also display wave-like properties. Okay, so it was de-Broglie, French physicist. His full name actually Louis Victor de-Broglie. Louis Victor de-Broglie. He put forward his bold hypothesis. So what do you mean by hypothesis? Hypothesis means strong, like some theory you give according to some logic, some logic, okay, according to some logic, rather than having strong experimental evidences. So that is called hypothesis. And when that hypothesis is being proved by experimental evidences, that will be established as theory. Okay, so anything, any idea based on strong logic can be a hypothesis, and when it is experimentally proved, then it is called theory. Okay, so de Broglie had put forward bold hypothesis that material particle when it is in motion, particle in motion may show or should display wave like properties. Okay, but then question will be what was like on what basis, like what was the basis of his this hypothesis, what is the logic behind that? So the logic behind that is, first logic is, see, in this universe all forms of physical, all physical form of this universe can be governed by two fundamental quantities, two fundamental quantities, those are mass and energy. So mass and energy, these are two fundamental quantity. Mass and energy are two fundamental quantity. So mass can be written as matter, and this is actually particle, sorry, energy, radiation. So energy can be identically called as radiation, radiation, and mass can be called as matter. Matter and radiation, these are the two things which actually can explain or governs all the physical forms of universe. Okay, and we have seen, according to Einstein's mass energy equivalence, E is equal to mc square. I hope you know this equation. This is called mass energy equivalence. Mass energy equivalence. I'll tell you what it is. Mass energy equivalence. What is mass energy equivalence? That means suppose some amount of mass is disappeared, in any experiment. That doesn't mean that mass is lost. It is converted to energy. Okay, mass energy conservation. So that's why mass, together mass and together mass and energy conservation rule had been stated by Einstein. That need, this is not only mass or not only energy. The proper conservation energy conservation law should be mass energy conservation law. What is that? If some form of mass or some amount of mass is getting disappeared in some experiment or some, like some natural phenomenon, then that equivalent amount of energy will be obtained. Equivalent amount of energy will be obtained. Suppose I have delta m amount of mass is disappeared. Okay, suppose I had in before some experiment or reaction, I had some m mass. Okay, now my mass has become less little bit by delta m. Okay, so where has that gone, this mass? This has been converted to energy. How do you get that equivalent energy? Using this equation, delta m into c square. You we will be discussing uh, when we'll learn about nuclear reactions, Q value, fission, fusion, all those experiments we will be learning, like all those phenomenon of radiation we will be learning. That time we'll see that how mass energy equivalence is there, and it is actually true that if some mass is getting disappeared, then equivalent energy will be created. Okay, this is called mass energy equivalence. That means, mass energy equivalence means, see, matter and radiation, they have matter and radiation, they have perfect equivalence. Okay, so according to this equation, we can get some equivalence between mass and radiation already. I told that energy can be equivalently thought as radiation and mass is matter. Okay, so matter and radiation, they have equivalence. Okay, so that is what we have seen. So there is a mutual symmetry between them. So if matter can be converted to radiation or energy, or maybe energy can be converted to particle, so they have perfect, they the like between this matter and radiation, they have mutual symmetry. Okay, mutual symmetry, that is what de Broglie argued. And the second argument he had, second, not the second, the same argument he had put forward, I have just broken into 2 points. One is this one, mass energy equivalence. Another one is nature always loves symmetry. So what is that? See, we have seen that nature is, okay, so wave is having dual nature, having dual nature, dual nature. I'm sorry, this radiation has dual nature, dual nature. Since this radiation and matter, they have equivalence, by symmetry, the matter also should show dual nature. Okay, so these were two strong argument or logic behind the hypothesis. What is the hypothesis? Now we'll learn what is the hypothesis. So according to the hypothesis, the waves, okay, so, or according to the hypothesis, the material particles in motion must be associated with waves. Okay, and these waves are called matter waves, matter waves or de Broglie waves, de Broglie waves. Okay, and according to his hypothesis, the wavelength associated with the material particle of mass m and which is moving with the speed v is given by lambda is equal to h by p or mv. I'll write it here. So wavelength, de Broglie's wavelength, according to the hypothesis, it is h by p or m into v. P is the linear momentum of the material particle. Linear momentum. Okay, P is the linear momentum. So that's why I have written a mass of the particle and v is the velocity or the speed of the particle. So according to de-Broglie's hypothesis, material particles in motion must be associated with waves, and these waves are called matter waves or de-Broglie's waves, and the wavelength is given by h by p. H is the Planck constant here, and p is the linear momentum of the particle. Okay, linear momentum of the particle in motion, and this is actually Planck constant. So you know h is Planck's constant. Okay, I'll just elaborate on this. So this wavelength is sometimes called de Broglie's wavelength. Okay, de Broglie's wavelength, de Broglie's wavelength. Okay, de Broglie's wavelength lambda. I'll write here. I'll clean it up. So de Broglie's wavelength is given by h over p or h by mv. Okay, v is the speed of the particle in motion. Sometimes it is denoted by d also, de Broglie, to denote it is a matter wave. So there are two waves actually. Waves, see, purely radiation has their wavelength, waves. So those are called electromagnetic wave or whatever. And this is actually matter wave. This is called matter wave or de Broglie's wave, and this wavelength is called de Broglie's wavelength. Okay. Now look, in this case, there are few things. So de Broglie's wavelength is, see, in this equation, this is called even de Broglie's equation. De Broglie's equation. De Broglie's equation. So this de Broglie's equation is very interesting. You look both left hand side and right hand side. What it is connecting? See, it is connecting two nature of the material particle or matter. Two natures. This is, see, wavelength is actually wavelength. This is wavelength is attributes of wave nature. Attribute of wave nature. Attribute of wave nature. Okay, and see, this is called momentum. Generally momentum is attribute of particle nature. Particle nature. Attribute of particle nature. So in the left hand side it is wave nature, and right hand side it is particle nature, and H is the breeze. So you can see this is the breeze which is connecting wave nature and particle nature. Wave nature is given by de Broglie's wavelength, and this is the momentum of the particle. So this equation, de Broglie's equation, is very interesting. It is actually connecting both the nature, left hand side wave nature and right hand side it is the particle nature. So momentum is always attribute, like gives the attribute of wave nature, and momentum is attribute of particle nature, and wave length is actually attribute of wave nature. Okay, now we'll see few more things with this equation. So lambda is equal to h by p. As you know, h is the Planck constant, so this is a constant term. So we can say that lambda is directly inversely proportional to the momentum of the particle. Momentum of the particle. What does that mean? That means if you plot de Broglie's wavelength with momentum, how you get? you will get hyperbolic curve like this. Okay, see again, P is equal to M into V. Okay, now let us see if we plot. So if we write this here, P is equal to mv, so lambda will be directly proportional to 1 by v if m is constant. Okay, f is constant. Okay, so now if we plot lambda with v, then also we get the same thing, but through this line it will be actually m constant, m equal to constant, m has a constant value along this line. Okay, similarly if we plot with mass, we'll get the same curve because lambda is directly inversely proportional to mass also if v is constant. So then we'll write here like this, and then look, we get here v constant, velocity is constant along this line. Okay, so this is what sometime de Broglie wavelength and momentum plot will be given in competitive exam. Then you have to see whether this is like this or like this or like this. There will be various very like many curves will be given. In fact, I have given you in the quiz questions. You may go and see there. Okay, one more thing is, see, we have seen, we have plotted in this way like lambda and p. But if I plot lambda by 1, lambda versus 1 by p, then it would give like this. Okay, it will be like this. It will go through the origin like this. Okay, it will be a straight line. In that case, it will be a straight line like this. All right. So now, since this is the lambda is inversely proportional to p, we can draw some conclusion or some important points from here, that if velocity, I have told you here, when the particle is in motion will be associated with a wave, matter wave. Why? When particle is at rest, whether that particle will be having any wave, de Broglie wave, we'll answer it here. If this is 0, then what is the wavelength? Wavelength tending to infinity. So what does this imply? This implies that wave associated with material particle, like, yeah, so waves are associated with material particle only when that that particle is in motion. So this wavelength infinity, de Broglie's wavelength infinity, like these are not not having any significance. If you have infinite any quantity, in reality infinity doesn't have any sense. That means in reality any quantity cannot be infinity. So if your v is 0, that means the particle, material particle, is at rest, then lambda tending to infinity, which implies that particle particle at rest won't be won't be associated with any wave. Okay, any wave. So this is the implication we get from here. One more thing is this, see, this waves. So you look here, lambda is inversely proportional to, or I can write as equal also. I can write h by p. H is a constant. All right. and this is mv. V is the speed of the particle. So look, lambda will be more if these are smaller quantity. Okay, this m and v are smaller quantity, then it will be more. That means value will increase more or increases. Lambda will be increasing. Okay, but if m, this mass and speed is very large, then so increases for small values of values of m and v. Okay, and wavelength would be shorter or decreases. It wavelength decreases for larger mass and speed. Okay, so that is what we can say, because speed and mass, they are in the denominator on the right hand side, and wavelength is inversely proportional to the momentum. So mass and velocity or speed both matters. So I'll just give you one simple example. You might be thinking that if material particle in motion or matter in motion could associate with de-Broglie wavelength, then maybe we are also sometime moving with 80 kilometer per hour or something like that. Okay, so whether a bus or a train even have further higher velocity, even a plane, whether they also have matter wave. So as I said, lambda is equal to h by p. That means h by m into v. Okay, so it matters on these particles. Sorry, these two quantities, mass and speed. How great this wavelength will be, or how small this wavelength will be. Okay, so I'll just give you a simple example. Suppose I have a ball of mass. Okay, a ball of mass 0.12 kg moves with 20 meter 20 meter per second speed. Okay, then what is the de Broglie wavelength associated with this ball? We have to find out. So de Broglie wavelength associated with this ball, lambda d associated with the ball. Okay, with this ball. Let us find out. See, this will be p. P means m into v. M is also given. V is also given. So, okay, I'll write it here. This is 6.63 into 10 to the power minus 34 joule into second divided by 0.12 kg into meter per second 20 meter per second. Okay, this will actually give you, see, kg meter per here, kg meter per second here. If you just break this see this joule is actually uh, acceleration, mass into acceleration. So from there, kg obviously will be there, m into a, sorry, ml square t to the power minus 2. Here it is like that, and also second is there, so t joule second, so it will be ml square t to the power minus 1. This is the dimension, and if you see here, This mass has m, meter per second has L, right? L per second means 10 to the power minus 1. So in the numerator this is, in the denominator m L t to the power minus 1. So t to the power minus 1 m goes from both sides. You will get L, 1 L will be there. So it will give you meter. Okay. So this will give you the unit meter. Joule means work done. So from there, force into displacement. So from there, you can find out the dimension and you can get this unit as meter. So look, this, how much you get. If you calculate this, you will get something like 2.7 into 10 to the power 2.76 into 10 to the power minus 34 meter. Look, this factor, it is actually 10 to the power minus 34. 10 to the power minus 34 means what? It is very, 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 very small. Okay, the wavelength is very, very short wavelength. Okay, very, very small or very, very short, or short wavelength. And such a short wavelength it is that we cannot even measure with instruments wavelength. Even with sophisticated instruments, we cannot measure this less length, this much less. Like, see, we can even go up to 10 to the power, like angstrom order maybe, 10 to the power minus 10 maybe. But we cannot measure up to now whatever available instruments we have. We may go up to angstrom order hardly, but we cannot go up to this much. So the de-Broglie, so what this implies? This implies that the de-Broglie wavelength associated with associated with the gross matter, or okay, gross matter or material can be written, having larger mass. Okay, gross matter or material is negligible negligible in length. Okay, in length. So we cannot measure that, or we cannot sense that wavelength. Okay, so that's why de-Broglie wavelength or matter wave, de-Broglie waves associated with subatomic particle is significant. Associated with subatomic particle, I'll tell you what it is, or quantum particle. These are called quantum particle. Subatomic particles is significant. Okay, is significant, or are significant. Waves are significant. Significant. So what are subatomic particles? Like, say, proton, electron, then neutron, alpha particle, etc. Alpha particle. These are actually subatomic particles. Okay, these are subatomic particles which has, the mass almost of the order of 30 kg, right? All of them almost like in this order. Like proton and neutron, that has 10 to the power minus 27. So this is very, very small mass. You look here, if I put lambda is equal to h by p, okay, h by p, p is, see, mass is already this much order, 10 to the power minus 27. Okay, so it will be here, it is actually Planck constant is 10 to the power minus 34. So it will be actually, at least you will get some angstrom order. Okay, some angstrom or angstrom order at least you will get, so which is still can be seen or can be measured with instruments. Okay, that's why whenever we talk about de Broglie wavelength or matter wave, we'll always give examples of electron, proton, neutron, alpha particle, these subatomic particles. Okay, because the wavelength associated, de Broglie's wavelength associated with subatomic particles are significant. Otherwise, see, we have seen almost of the order of 10 to the power 34 meter, so which is very very negligible and very very small, which we cannot even measure. Okay, and one more thing is here, the matter wave, we have to very very carefully understand this. Matter wave is given by H by P. Okay, and what about electromagnetic wave? It is actually given by C by nu, C by nu, or frequency of the electromagnetic radiation. See, in this case, this is electromagnetic wavelength. This is called electromagnetic wavelength. Electromagnetic magnetic wavelength. Okay, and this is actually called matter wave or matter wavelength or de Broglie wavelength. Matter wave or de Broglie wave, and this is called actually electromagnetic wave. De Broglie wave are waves. De Broglie's wave is not electromagnetic wave. Okay, I'll give you one more good idea or good concept over here. Whenever we talk about, see, if the lambda wavelength, de Broglie wavelength is given for a material particle, material particle, and you have been asked to find out what is the energy of that particle. Suppose an electron has de Broglie wavelength lambda. What would be the energy for that? You cannot write hc by lambda with this. Okay, you cannot write energy is equal to hc by lambda for matter wave. You cannot write this. Just remember this because there are questions related to this concept in the competitive exam. Okay, so if suppose the energy is given for photon, some radiation, electromagnetic radiation, and for some material particle, both are having same energy, does not mean that they will have same de Broglie wavelength, because you cannot write hc by lambda for de Broglie wavelength. So when de Broglie wavelength is given, if you want to find out energy, you will be able to find out kinetic energy from there. Look how you get de Broglie wavelength is given as h by p. So you will be able to find out what is p from here. Momentum. Once you know the momentum, then you have to do ek, kinetic energy, or sometime it is given by k also. So it will be given by p square by 2m. Okay, this is how you can find out the energy of material particle for which the de Broglie wavelength is given. But suppose the wavelength for any electromagnetic radiation is given, then you can find out energy from there, hc by lambda. Like you have h nu, so nu you replace by c by lambda. So hc by lambda will be the energy of the electromagnetic radiation or electromagnetic wave. So matter wave or de Broglie wave is not an electromagnetic wave. Okay, so these are the few points. I'll take up few examples on this concept also. Okay, sometime later, maybe next class we'll take up examples on this chapter related to photoelectric effect and this dual nature of matter and radiation. Deepa, are you understanding what I'm trying to say? You can always ask me. If you don't understand, you can stop me anywhere you like. So we'll just see how to calculate de-Broglie's wavelength for different cases. Now we'll take few cases where how we can calculate de-Broglie's wavelength for few cases. Okay. Suppose first case. Okay, let me write as one. So this is case one. Suppose an electron has kinetic energy given. Okay. So how to calculate? I'm just I'm just teaching you now how to calculate de Broglie's wavelength for different cases. Suppose you have been given an electron which has kinetic energy, some k value is not given. Suppose this is k, kinetic energy k. Okay. So how to find out de Broglie wavelength? We know de Broglie wavelength is h by p, which is h by m into v. V is the speed, and you have been given kinetic energy. Kinetic energy means half m v square, right? So let us write curly italic only. So half m v square. This is the kinetic energy for the electron given. So I'll write suffix m. E is the mass of the electron, and this is the speed v. So you have to find out m into v, okay, or momentum from this kinetic energy, so that you can find out the de Broglie wavelength. Okay. So let us see how to do that. What I will do, m into e v square will keep, and we'll write this way, multiplying 2 with kinetic energy given. Now look what further we can do is m e square v square by me. See, this me suffix is for mass of the electron. Okay. All right. So here one mass was there. I have taken two masses, m into me into me. So I have divided with one me. So this is 2 into k. So this part is m v square, that is p square, right? This is p square. Now I can write this m into v whole square. This is m into v whole square, which is p, right, in the numerator. And this is actually 2m e into k. So what we have got from kinetic energy, see, if the kinetic energy given, we can find out the momentum in this way. P square by 2m is equal to kinetic energy. So see how we can write. If the kinetic energy given, we will write directly p square by 2m, whether it is electron, proton, or whatever it is. We can write kinetic energy p square by 2m is equal to kinetic energy. Okay, kinetic energy. This is actually kinetic energy. Okay, k, kinetic energy. Oh, all right. So if this is given, then p is equal to root over 2m into kinetic energy. Okay. So then we can put it here is by p. P means what we have got. We have got under root 2m into k. K is the kinetic energy given, and see, this kinetic energy can be given in different form. I'll tell you. This is m, mass of the particle, given subatomic particle, whether alpha particle, electron, proton, neutron, whatever it is. Okay. So this is how, if the kinetic energy is given, you have to write h by root over 2 into mass of the particle and the kinetic energy of the particle. Okay. Under root 2 into mass into kinetic energy. Okay. So this is what you have to do. Now the case 2, I'll tell you. See, sometime kinetic energy will be given double, triple, and everything. So then see, suppose there is an electron which has some kinetic energy, but now kinetic energy is being doubled. What will be the wavelength? See, in the beginning wavelength was h by under root 2m kinetic energy. Okay, now the kinetic energy is being doubled. That means, see, if I write the wavelength is lambda 2, this is 2m and 2k. Okay, that means see, you get h by root over 2mk was already there, and 1 by root 2. Okay, so this is what, if the kinetic energy is being doubled, then this is happening. If it is 4 times, then it will be half of, see, then this is actually given as lambda 1. So lambda 1 by root 2. If it is 4 times, then you will get half of the wavelength. Okay, that means when you increase the kinetic energy, the wavelength will be decreasing. Suppose there is an electron. See, some cases like in electron microscope, in modern times, modern age, we use electron microscope for various experiments in the scientific laboratory. That is called transmission electron microscopy, or many others are there, which uses, like, instead of light, you use electron as the probe. Okay, so microscope generally uses light, as far as you know, but you will see in the higher classes that electron also can be used as probe, in just replacing the light by electron. So you might be thinking, how can we see with electron? Because electron has a wave, photon has a wave. So you can see with this actually the de-Broglie wavelength. Okay, so it will be associating with de-Broglie wavelength, and that wavelength will interact with the matter. Okay, it will act as a wave. Okay, so those are actually of higher topic. So if you want to like decrease the wavelength of the electron, then what you have to do, you have to accelerate, or you have to give greater speed or greater kinetic energy to that electron, so that you can decrease the wavelength. All right, so now see, how do you give energy, see, kinetic energy to an electron? We have already learned in the potential chapter, like second chapter or maybe third chapter, we have already learned how to accelerate an electron. Suppose you have a region of space like this, and there is a potential difference between this region. So potential is 0 here, and here is some v. Okay, so there is a potential difference between these two lines. Okay, this region has, so that means it has some electric field. So whenever there is an electron resting over here, when there is a potential difference in this region, then electron will actually experience a force, and it will be actually accelerated. Force is applied means it will have some acceleration, so it will be accelerated through this region. Okay, if suppose the electric field has direction in this way, so electrons will be actually accelerated in this way. In the opposite direction, it will be accelerated in the sense it will be having, see, if suppose initially the speed was 0, then it will have a final speed. Some speed will be there. When it see, when it goes from here to here, it actually acquires some speed. Electron acquires some speed, or we can say in other words, it will actually gain some kinetic energy. So if you have to give some kinetic energy to an electron, not only electron, any charge particle, you can accelerate them through a region where there is a potential difference. Okay, because, yeah, so this is the thing. Now if you suppose you have applied some v volt between this region, okay, v volt, then what will be the energy, kinetic energy gained by this particle? Suppose electron, I am taking electron has mass me, one single electron. So the electron will actually have kinetic energy. Look, kinetic energy, I'll write arbitrarily half m e B square. And this kinetic energy is given by E into capital B. What is this B? This B is the applied potential difference. Potential difference, okay? Potential difference. So this B is potential difference and this is the electronic charge. So this will give you the energy and this is also having kinetic energy. So the kinetic energy, if an electron, so I have told you first case was that if you know the kinetic energy of any particle, then you can write down or you can calculate the de Broglie's wavelength just by writing h by p. P can be replaced by root 2 m into k. Okay, mass into kinetic energy. Now kinetic energy is not given in like directly, it is given indirectly. If suppose, so case 2 is, if suppose if an electron is accelerated by v volt potential difference, okay, then for that case, see ev, we can write e into v is equal to kinetic energy, or we'll write, yes, e into v is equal to kinetic energy. If you want to further elaborate, you can write e into v is equal to half m into v square. So from here, see, in place of kinetic energy, if you write just ev here, just write ev, that's all. That's all. You don't have to do further. Okay. I'll just, I think I have to stop with this kind of concepts. I think I'll just go with few more things. Experimental evidence I will go in the next class maybe, and then I'll take examples also, numerical examples. So here, see what I have told. Kinetic energy can be just replaced by E into V, electronic charge into the potential given, potential difference given. Okay. Here one nice thing is there. I'll just write here. That's why I'm just. So you just think that in the second case, some voltage is given. So your kinetic energy can be replaced by E into V. So wavelength, de Broglie's wavelength can be written as h by root over 2 into m of the particle into E into V. Okay. So suppose this is electron. If this is an electron, if this is an electron, okay, if this is an electron, see, we can just put the value of h is 6.63 Planck constant into 10 to the power minus 34 joule second, and if this mass is taken as 9.1 into 10 to the power minus 31 kg, and E is, see, the small e, if you put as 1.6 into 10 to the power minus 19 coulomb, and V as volt, V in volt, then look, it has a simple formula. If you put all those things, then, so you just leave this V volt. If you put this H, M, and electronic charge, etc., if you put, what we get, you will get a simplified formula. Look, I'll just write once again. H by P, that means H by root over 2 into M into V, E into V. This can be written as 12.27 divided by only capital V, V in volt. Okay. If you write V in volt, you will get this as angstrom. Okay. You will get this as angstrom. Okay. Sometime it is written 12.3 also. So you'll get in the unit of angstrom. Understand? So this is very, very important shortcut method to calculate de Broglie's wavelength in the competitive exam. If you are given certain potential, suppose 100 volt, so it will be, say suppose 100 volt electron is accelerated through 100 volt. Then you just put it here 100 volt. So you will get 12.27 divided by 10. So you'll get 1.27 angstrom. Okay, 1.2723. Suppose 1.23 angstrom here. Okay, so this is how simply. So we have learned two things. One is lambda is equal to h by 2m k. Second formula we have learned, lambda is equal to h by root over v. Okay, sorry, this is not uh, h. Now it is 12.27. This is angstrom if this is in volt. In volt. If you are given 10 kilovolt, then you have to write this into 100. Okay, then you have to divide with 100. Yeah, so whatever you get. So these are things you can utilize during calculation of, yeah, de Broglie wavelength. Now I'll just tell you one more thing here. Suppose some thermal neutron or any material matter, okay, any thermal neutron. If you give some heat to an electron, then it will actually be vibrating and it will have kinetic energy. Vibration, vibrational kinetic energy. So in that case, there are certain, like you have to see if you have a material given some kind, see, some thermal energy in terms of K into T. T is the temperature. Suppose a material or metal has been heated to some 300 Kelvin or something. This is in Kelvin, okay? So K 300 Kelvin. Then what will be the de Broglie wavelength? Some electron has been heated with this like that. So in that case, you have to write kinetic energy is equal to only kT. Kinetic energy will be only kT, or I'm sorry, this may be half kT. Okay, when we'll solve problem, we'll just clarify this again. But in case of, okay, so average kinetic energy of neutron in absolute temperature. No, this will be 3 by. Okay, let me tell you. I'll just give you the correct expression for that. So I'll just tell you what it is. Suppose a neutron is actually heated to some absolute temperature. So average kinetic energy of suppose a neutron, thermal neutron, average kinetic energy. Even electron, for case of electron also the same thing. Average kinetic energy of a neutron at absolute temperature. Absolute temperature means in Kelvin. Okay, so then kinetic energy can be written as half m neutron mass into v square is given by 3 by 2 kT, 3 by 2 kT, or you can write this even p square by 2 mn is equal to 3 by 2 kT, 3 by 2 kT. So 2 goes off. So p is equal to under root 3m k. K is the Boltzmann's constant, okay? 3m kT. This you know from thermodynamics, okay? So if some temperature is given, in case of temperature, you have to write P is equal to 3m kT. So average kinetic energy of a neutron at absolute temperature, okay? Absolute temperature. So in that case, you can write, see, in place of kinetic energy, you will be writing this H by P. So H by P means H by root over 3m k. K is the Boltzmann's constant. I am writing kb, Boltzmann's constant, into T. Okay. So in this case, you have to remember what is the value of, maybe value of the Boltzmann's constant also will be given sometime. or else you have to remember. Okay, so if suppose kinetic energy, kinetic gas, so in case of gases, in case of gases, sometime you can write PV is equal to RT and all those things. From there also you will be able to find out like some expressions. We'll just take up examples. That time I'll tell you again in detail. Okay, so I'll just finish with a simple uh, concept here. One more concept. So we have learned. So these are few expressions which we can use to calculate de Broglie's wavelength for various conditions, like various cases whenever say thermal neutron. In case of thermal neutron, you can write like this. In case of electrons or any charged particle accelerated with potential difference, you can write this. If the kinetic energy is directly given, you can write this to calculate de Broglie's wavelength. Now see if such an if some particle if some particle subatomic particle atomic particles have speed comparable comparable to the speed of speed of light, that is c, then 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 v has to be replaced by, so see the expression has to be replaced by relativistic expression, okay. So for that case you cannot directly write v, you have to write, see, v has to be replaced by, or mv I'll write. So then see mv has to be replaced by rest mass m0 v divided by 1 by root over v square by c square, this factor. So momentum has to be replaced by this, okay. So this is rest mass, like see this is called relativistic effect. Relativistic effect is that when any particle has a speed comparable to light, then its mass cannot be exactly, see, its mass becomes relativistic. That means mass actually will not remain the same. Suppose electron has mass 9.1 into 10 to the power minus 31 kg, but if it is accelerated or it has a speed of some 0.5 c, so in that case we can write m into this c for calculating momentum, okay. For that case this mass can be used, this is called rest mass, but with a factor this. So mass becomes relativistic, so you have to write in that case mass relativistic mass into v. The speed is already given, v is equal to 0.5 c, okay. 0.5 c you can write, this is 0.5 into c, 0.5 into c, here also 0.5 into c whole square, so c square goes up 0.5 square you will get here, okay. So in fact you have to just remember that whenever the speed of the particle, subatomic particle is given which is comparable to speed of light, then the mass will not be the same mass, so it will be a relativistic mass. So that's why p relativistic, p will be relativistic, momentum will be relativistic, so that momentum has to be replaced with m0 v, whatever speed is given, divided by b square by c square. In fact, this is actually p, whatever momentum. See, generally we get, so this will be used as this only, rest mass only, 9.1 into 10 to the power minus 3, 31 kg only, and the v will be 0.5 c as I was telling you. And in this factor also has to be written in the denominator. So the momentum mv has to be replaced by m0 into v divided by under root 1 minus v square by c square. Okay, so with this I'll stop here today. The next day I'll take various kind of numerical problem, whatever I discussed today, whatever I have discussed today, and also in the previous classes related to photoelectric effect, etc. I'll take up various numerical problems on those topics. Okay, so Deepa, you can read the whole chapter and be ready for solving various problems. Okay, and while discussing so that you can understand, so you have to be thorough with the theory part. And I have just left out with this small part, that is experimental evidence or demonstrations for the wave nature of the electron. So as I said, de-Broglie had given this as hypothesis, but someone had to prove later, that is Davison and Germer, and also G.P. Thomson. They had actually proved from electron diffraction experiment through nickel crystal. They have done diffraction. We have learned. We have studied with light, isn't it? So we need wave nature, isn't it? For uh, experiencing or for seeing the phenomena of diffraction, you need wave, right? Wave theory, wave fronts, if you remember. So this G.P. Thomson and Davison-Germer's experiment is actually there in your initiative textbook. We'll discuss that. So they had actually done the experiment, diffraction experiment, electron diffraction experiment, and that's how they proved that electron has wave nature also. Okay, so electron diffraction at nickel crystal we'll discuss on the next day. That time you will understand again better, and then we'll take up numerical example. Okay, after discussing this experimental demonstration of wave nature of electron. Okay, so with this I stop here. So if you have any doubt, you can ask me now. Do you have anything to ask, Deepa? Or else we'll stop it here. Okay, you can ask me in the next class also if you have something. Okay, I'll stop it here. Bye for today.